In the previous class, we spoke about the blackbody emissive power, and we wanted to see what is the relation between the blackbody emissive power, commonly denoted by E b lambda at a given temperature, with the blackbody radiation intensity, and the relation which we have obtained considering a blackbody of unit area placed at the center of a hemisphere and measuring what is the total energy emitted per unit time, per unit area, per unit wavelength by a blackbody into the hemispherical space, we have obtained the relation between the emissive power and the intensity of blackbody radiation. So, the relation that we have obtained is the following, where the E b lambda t is the spectral blackbody radiation flux, which is essentially the energy emitted by a blackbody at any given temperature T. We need to remember that this T, the temperature in radiation, is always refer to the absolute temperature per unit area, per unit wavelength, about that wavelength lambda, per unit time. So, this relation between the spectral blackbody radiation flux and the radiation intensity are simply this pi times the radiation intensity is the blackbody emissive power, which has units of watt per meter square per micron, where this micron refers to the wavelength of the radiation, that wavelength of the radiation. If you remember the units of I b lambda t, that has units of watt per meter square per micron per steradian, but since we have integrated this over the entire hemispherical space, taking into account the variation of the angle, so therefore, this E b lambda t does not contain any any solid angle. So, if this is the formula, and we already know what's going to what is, through use of Planck's function, what is the expression for I b lambda t. So, using the Planck's function for I b lambda t, one can write E b lambda t as in this form. So, this is in watt per meter square per micron again. The only thing that we have done in this expression is substituted the expression for the intensity from Planck's function, which we have discussed in the previous class. So, when you do that, then you get this expression for the blackbody radiation flux, and the C1 and C2 are constants. So, C1 is simply twice pi h Planck's constant, c the velocity of light, and you calculate the value of this constant, and similarly C2 is h c by k, all of them have the usual meaning. So, this is the value of that constant. So, what this tells us, what this expression tells us, is that at any given temperature and at any given wavelength, E b lambda t can be computed. So, not only you can, and so E b lambda t is a function both of temperature and of wavelength, and therefore, if we know the wavelength and the temperature, the blackbody radiation flux can be computed. So, provided we know what is the temperature, then the spectral blackbody emissive power. I use the word spectral here purposefully to stress that the blackbody radiation intensity will also depend on the wavelength at which we are measuring the radiation flux. So, all these are strongly dependent on the wavelength. Therefore, since we know now we know what is the relation between E b lambda t, which is the blackbody radiation flux, with lambda and t, we can plot the blackbody radiation function as a function of lambda, the wavelength, at different values of temperature. Once again, E b lambda t is a function of wavelength and is a function of temperature. So, keeping one constant, in this case the temperature constant, I can compute the variation of E b lambda t with lambda, and then I can choose another value of temperature and again compute the same variation of EB lambda t as a function of lambda. So, I get a series of curves, the series of curves at different values of temperature, which shows the variation of the blackbody radiation flux as a function of wavelength given by the expression which is shown over here. So, I fix lambda, I fix t and plot EB lambda as a function of lambda, and then I choose a different value of temperature and plot this again. Therefore, this would result in a family of curves which would look something like this. So, the variation of E B lambda t as a function of wavelength will show variations like this. So, these are at different values of temperature T1, T2, T3 etc., and this T1 is greater than T2, greater than T3, greater than T4 and so on. So, the top curve corresponds to the highest temperature, the bottom curve corresponds to the lowest temperature. So, if these maxima, the point at which the EB lambda is maximum, that means the blackbody emissive power is maximum if these points are joined together. The locus of this line is very interesting. It is lambda t corresponding to the maximum value of EB lambda t is simply a constant 2897.6 micron times Kelvin. The always in radiation, the wavelength is referred to as wavelength is expressed in microns and T is in kelvins. So, I will go through it once again. Using the formulation that what we have written in the previous slide, let me write it once again here. Some constant C1 by lambda to the power 5 exponential this is the formulation, it is in watt per meter square per micron. Using this formulation, I fix temperature. Let us say I have taken the temperature to be equal to T1 here, okay, and this is T2, T3 and T4. So, if I fix T1, I can plot EB lambda t as a function of lambda. This is its variation. Then I fix the temperature at T2 slightly lower than T1 and compute this function once again, and this is what I am going to get corresponding to T2. Then T3, which is less than T2, this is the distribution of EB lambda t as a function of lambda. Interestingly, when you look at the maxima of these curves, what you see is that the product of lambda times t corresponding to the max of EB lambda t is a constant. So, if you find out what is the corresponding lambda and what is the value of T4, if you multiply them together and you find out what is the corresponding lambda and what is the corresponding temperature T1. So, essentially it would tell you that lambda 1 T1 corresponding to the maximum of this must be equal to lambda 2 times T2 corresponding to the maximum of EB and so on, and this relation that lambda t corresponding to maximum EB lambda t is a constant is known as Wein's displacement law. So, what it states is that if you know the temperature, then the corresponding value of the wavelength at which E b lambda t is a maximum can be simply obtained by this relation. We will see its use in subsequent analysis, but let us do something which is even more which we know even better. So, the radiation energy that is emitted by a black body at t over all wavelengths. So, the expression that I have, this is the radiation emission by a black body at a specific wavelength. But we probably are more interested in finding out what is the total energy emitted by the black body over all possible wavelengths. So, mathematically speaking, I would like to know what is the total energy emitted by the black body over a wavelength from range of 0 to infinity. So, if I could find out the total, if I would like to find out what is the total energy emitted by the black body, then the spectral black body radiation must be integrated over all possible values of wavelength. So, to convert from E b lambda t to E b t, which does not have any lambda, that means I must have taken care of all the lambdas possible. So, in order to obtain E b t from E b lambda t, I need to integrate E b lambda t over all wavelength. So, that is how you obtain the total amount of energy emitted by a black body at an absolute temperature of T, which is what we are going to do next. So, if you do that, if you are trying to find out at all wavelengths, then E b t is from lambda equals 0 to lambda equals infinity, and the expression for E b lambda t, which is this times exponential since what we are just saying that this must be equal to integration from 0 to infinity E b lambda t times d lambda. That is a standard definition, and instead of E b lambda I have put the expression incorporating Planck's distribution. So, this integration can simply be evaluated by saying that let some quantity x to be equal to lambda times t. So, your E b t is going to be equal to t to the power 4 x equals 0 to x equals infinity, and this is C 1 by x to the power 5 exponential C 2 by x minus 1 times d x. And when you do this, when you perform this integration, since it is a definite integral, once you evaluate the integral, it is simply going to be a constant, and this E b t, this constant is expressed as sigma, and you have t to the power 4. So, this is probably the most common radiation expression that you have seen before, and this is watt per meter square. So, the expression, the unit for E b lambda t is watt per meter square per unit wavelength, which is in micron. Since you have integrated it over all possible wavelength, so therefore, this one will not have this micron over here, it is simply watt per meter square. And this sigma you are well aware of, this is known as the Stefan-Boltzmann constant. Stefan-Boltzmann constant, and the value of this sigma is 5.67 into 10 to the power minus 8 watt per meter square Kelvin to the power 4, and this relation obviously then is known as the Stefan-Boltzmann law. So, this is one of the unique laws of radiation, which tells you that the total energy emitted by a black body at an absolute temperature T per unit area per unit time is a function of temperature, absolute temperature to the power 4, and the constant of proportionality is simply sigma, which is a constant which can be evaluated by evaluating this definite integral, and it has a numerical value of 5.67 into 10 to the power minus 8, and this sigma is known as the Stefan-Boltzmann constant. So, what we then see is there are two interesting observations from here. The first of all, that the black body radiation function, the emissive power of a black body is a function of wavelength and is a function of temperature. Since it is a function of wavelength, so that is why the emissive power of a black body, we use the adjective spectral before it to underscore the importance of wavelength while specifying the emissive power of a black body. Now, when you integrate it over all possible wavelengths, what you get is the total emissive power of the black body at that given temperature. So, it is the amount of energy emitted by a black body per unit area per unit time over all wavelengths possible. So, that is why it is total, and I can drop the spectral from the description of the emissive power the moment I integrate over it, and the result of this integration is the Stefan-Boltzmann law. In some applications, you are interested to know what is the total power emitted by the black body. You are more interested to find out what is the power emitted by the black body within a certain wavelength range. Let us say you would like to find out between 2 to 4 micron how much of the energy is going to be concentrated. So, the entire black body emits radiation starting at lambda equals 0 to lambda equals infinity, but you do not want that. You want within a specific range of lambda how much of energy is going to be released, how much of energy is going to be emitted by the black body as a fraction of the total energy emitted by the black body. So, this is an important parameter which we will keep on using in our subsequent discussion. That means, the fraction of energy emitted by a black body within a specific wavelength range. So, that is known as the black body radiation function. So, we would see what is a black body radiation function. So, black body radiation function, as I have expressed to you, so it is between and wavelength from 0 to lambda at a given temperature is the amount of energy emitted by the black body between 0 to lambda divided by 0 to infinity. That means, the total energy emitted by the black body at that given temperature. So, once again the fraction, the black body radiation function, the fraction of energy which is emitted by the black body within a wavelength range from 0 to lambda is nothing but the amount of energy emitted by the black body between 0 to delta divided by the amount of energy emitted by the black body over 0 to infinity. So, this is the total energy, and this is the amount of energy within a fixed wavelength range. So, from Stefan-Boltzmann's law, we know that this is simply going to be sigma t to the power 4, and the numerator would be like this, T times d lambda. So, if you can introduce the expression of E b lambda t, which was as before this expression that we have obtained, C 1 by lambda to the power 5 exponential C 2 by lambda t minus 1. So, when you put this one in here and you do the analysis, what you would get is f 0 to lambda is C 1 by sigma x equals 0 to lambda t dx by x to the power 5, the same way we have done before, exponential C 2 by x minus 1. Okay. So, again I have used that x equals lambda times t, and the way we have done it for the Stefan-Boltzmann equation, this is what you are going to get. Of course, here also you would see that it's a function, this fraction is a function of lambda and a function of t as well. So, this integral can be evaluated, and f 0 lambda at t can be calculated for a given t, given lambda t. Okay. So, you in your text, I guess the idea behind this is very clear to you. I am trying to find out the fraction of energy which is emitted by the black body that is going to be concentrated within a wavelength range of 0 to lambda. So, if this is a fraction, then this is going to be the energy which is going to be within 0 to lambda by the total energy emitted by the black body. Total energy emitted by the black body is nothing but a sigma t to the sigma t to the power 4, and this can be substituted by the Planck's function as we have done before. When you incorporate that, you get the fraction in this form. This is again an integral equation which can be evaluated provided you specify lambda and t. So, once you specify lambda and t, this fraction can be evaluated. So, this fraction is calculated for a given lambda times t, and you would see that the results of the fraction is provided in a table. So, in that table, the total emissive power of a black body which is contained within the wavelength range is provided as a function of t and as a function of lambda. So, you must keep in mind that this t is always going to be in Kelvin and lambda is going to be in micron. So, if you look at the table now, the table here shows you the value of lambda t in micron, and this is E b lambda divided by t to the power 5. This is how the fraction is expressed. This is how it's shown. So, you know what is lambda t? Let us say you pick a value of lambda t to be over here. Lambda t is 2777.8. So, any combination of lambda and t which gives the product to be about 2777, it would give you a value of the f as 0.22. So, let us write it over here. If I write it in this, so for a value of lambda t equal to 2777, the value of the fraction is 0.2285. So, for lambda t equals 2777.8, the value of f is going to be equal to 0.22, 0.22. So, which means is that you choose some value of lambda and t, the product comes to close to 2777.8. So, if that is the case, then within that wavelength range at that given temperature, you can find out what is the fraction of energy that is emitted by the black body is contained within the wavelength. I think it would be more clear to you once we solve a problem using the table, and this f, the Blackbody radiation function, the table of Blackbody radiation function you can refer to and find out that given the value of lambda and t, what is the fraction that is going to be, what is the Blackbody radiation function. So, we will quickly solve one problem, and I think that would clarify any remaining doubts that you may have. But fundamentally, we are finding out the fraction of energy which is contained within 0 to some lambda at a given temperature for the Blackbody emission. So, let us quickly solve one problem, and then we will move on. So, what the problem says is that the emission is from a surface, from a Blackbody at T equals 1000 Kelvin. The first part is what fraction of the total energy is emitted below lambda equals 5 micron. Okay. So, what we need to do then is my lambda is 5 micron, T is 1000 Kelvin. So, lambda T is 5000 micron times Kelvin. So, when it says fraction, so I would like to find out 0 to 5 micron. The value of the Blackbody radiation function between 0 to 5 micron, fundamentally what this tells us is f 0 to 5 is the fraction of the total energy that is emitted by a Blackbody at a given temperature between the range 0 to 5 micron. So, from the adjoining table, I need to find out what is the value of 0 to f of 0 to 5 micron. So, for which case lambda t is 5000 micron Kelvin. So, if you look at the value over here, for a value of lambda t to be equal to 5000 micron Kelvin, the value of f is 0.66371. So, from the table I read that this is equal to 0.6637 for lambda t equals 5000 micron Kelvin, which simply tells me that 66.4% or 0.664, the fraction 66.4% of the total energy is emitted by the Blackbody at 1000 Kelvin below lambda equals 5 micron. That means, this is the value of the fraction. The second question is what is the wavelength below which the emission is 10.5% of the total emission at 1000 Kelvin. So, it is the reverse of the previous problem. In this case, f 0 to the unknown lambda at a given temperature of 1000 Kelvin is provided to be 0.105. We need to find out what is the value of lambda. So, once again, the emission is 10.5% of the total emission at 1000 Kelvin. So, the fraction of energy which is contained between 0 to the unknown lambda at 1000 Kelvin is specified to be 0.105. We need to find out what is the value of lambda for such a case. Once again, we look at the table, and when we look at the table, now we have to look at lambda t to be equal, the fraction to be 0.105. So, when you look at the fraction to be 0.105, you read the value of lambda t to be 2242.2 micron Kelvin. So, this refers to the value of lambda t. This you read from the table to be equals 42.2 micron Kelvin, and since you know the temperature to be equals 1000 Kelvin. So, therefore, your lambda is simply going to be 2.222 micron. So, at 2000 Kelvin, at 1000 Kelvin, the emission is going to be 10.5% of the total emission at an wavelength of 2.2 micron. And the third one is what is the wavelength? What is the lambda at which the maximum spectral emission occurs at T equals 1000 Kelvin. So, the third question is, what is the wavelength at which you are going to get the maximum spectral emission? The moment I say spectral, that means it's wavelength dependent. So, the value of the temperature is provided to you, you have to find out what is the wavelength at which the emission is going to be maximum. So, of course, the law that we need to use for this is Wein's displacement law. The Wein's displacement law simply states that lambda times T is a constant when we are talking about the maximum spectral radiation intensity at a given temperature. Since the temperature over here is provided, we need to find out what is the lambda in this case. So, this problem can simply be solved using Wein's law as lambda times T corresponding to the maximum emission is 2897.6 micron Kelvin. So, for T equals 1000 degree, this lambda would simply be equals 2.8976 micron. So, therefore, if your temperature is at 1000 Kelvin, then the spectral maximum of emission from a black body at 1000 Kelvin will take place at a wavelength of 2.8 micron. So, what we have discussed, if I would like to do a summary of this, is that looking at the black body emission and incorporating the Planck's formula in it, we have derived the Wein's displacement law, which shows that the product of lambda and T corresponding to maximum spectral emission from a black body is a constant, which is 2897.6 micron Kelvin. Secondly, the spectral emission, if you would like to convert it to the total emission from a black body over all possible wavelengths, that would give rise to the well known Stefan-Boltzmann law, where the proportionality between the emission and the temperature is E is proportional to T to the power 4, and the proportionality constant is Planck's constant. Next, we wanted to know the fraction of energy which is emitted between a certain wavelength range as compared to the total energy emitted by the black body over all wavelength range. So, this black body radiation function is evaluated for different values of the product of mu and t, lambda and t, different values of the product of the wavelength and temperature. So, these blackbody radiation functions provide us with the knowledge of how much of energy is going to be emitted by a blackbody at a given temperature within a specific range of wavelengths. And we have solved the problem, numerical problem, which I think would clarify any doubts that you may have in the use of Wein's displacement law, the Stefan-Boltzmann law and the blackbody radiation function.